Good morning. Today I'm going to discuss about our project, which is human activity recognition using PA Map 2 dataset. My teammates are Punitha Vancha and myself, Sai Bharath. Today I'm going to discuss these contents. Have you ever wondered how your smartwatch knows whether you're walking, running, or just sitting still? That's a thanks to a field called Human Activity Recognition or HAR. This technology uses data from sensors like those in your watch or fitness tracker to figure out which activity you're doing. But HAR isn't just about fitness tracking, it has real world applications that make a difference in people's lives. For example, it can help doctors monitoring patients recovering from surgery, assist in elderly care by detecting falls, or even support personalized health and wellness programs. In our project, we worked with a dataset called PMAP2, which records various activities like walking, running, cycling, and more. The data comes from sensors placed on the body, capturing detailed movements in real time. Our goal was to use this data to create a system that can accurately identify what activity a person is performing. By exploring this dataset, we are helping to bridge the gap between raw data and practical solutions that can improve health, safety, and everyday life. This project is about showing how understanding human movement can lead to smarter, more responsive technologies that benefit everyone. Let's dive into the dataset at the heart of our project, the PMAP2 Physical Activity Monitoring Dataset. This dataset was designed to capture various physical activities using sensors worn on the body. It includes measuring from three key locations: hand, chest, and ankle. The dataset captures movement data from 9 subjects engaged in 13 distinct activities, ranging from walking, cycling to more complex activities like vacuum cleaning or rope jumping. And what makes this dataset interesting is its richness, comprising over 2.8 million records and 54 features, including acceleration, gyroscopic data, magnetometer readings, and temperature. This variety allows us to capture both the movement and context of the activity. At the same time, working with this dataset isn't without challenges. It's a high dimensional dataset, meaning there's a lot of information to process and it has missing data points that require careful handling. These challenges make it a perfect test bed for building robust activity recognition models. Our exploratory data analysis highlighted some important aspects of the PMAP2 dataset. The activity distribution shows the activity 0, representing the transition state, is the most frequent one. And this reflects natural transitions between activities, and we have decided to keep it in the dataset to maintain the sequential flow and capture real world scenarios. We also explored the sensor features. Acceleration and temperature readings shows the distinct patterns for different activities. For instance, hand temperature has clear density peaks during stable activities, while hand acceleration shows more variability across movements. Correlation between sensors revealed additional insights. Sensors on the same body part, like the hand accelerometers, exhibit strong relationships. Cross body correlations, such as those between the hand and the ankle, are weaker but still provide valuable information. The temporal nature of the data is another key aspect. Time series plot shows distinct activity transitions, emphasizing the importance of sequence aware models. Finally, we identified missing values in certain features while we addressed the pre processing stage to ensure a complete and accurate dataset for modeling. Our data preparation phase focused on ensuring the dataset was clean, consistent, and ready for modeling. Missing values can disrupt analysis, so handling them was a key step in our preparation. We noticed missing data in various sensors and the heart rate column, which was entirely. And to address others, we started with the group mean imputation. This involved calculating the average value for each activity and subject pair and filling the missing data accordingly. Next, we used KNN implementation technique. Here, the algorithm used the similar patterns from other correlated sensors to estimate the missing values intelligently. Finally, we removed a very small number of groups, those with 100% missing data, like subject 4 performing activity 5, which couldn't be recovered. And after all these steps, we verified that there were no more missing values, ensuring our dataset was complete and ready for the next phase. After handling the missing values, we moved on to refining the dataset. So first, we standardized all sensor features to ensure consistency across the data. Standardization puts all values on the same scale, avoiding any one sensor from disproportionately influencing the results. Initially, the dataset contained 24 activity IDs, but not all activities were present in the data. Some activities, like watching TV, weren't recorded at all. So, to streamline the analysis, we adjusted the activity IDs to reflect only 13 activities that were found to be in the data, creating a clean and efficient mapping from IDs to descriptive labels like walking or cycling. Finally, we reduced the dataset's dimensionality using principal component analysis (PCA) that identifies the most important features in the data by combining correlated variables into principal components. This helped us to retain 95% of the data's variance while reducing the number of features, going from 54 to around 30. This reduction made the dataset more efficient and faster for modeling without losing meaningful information. Next part will be continued by Punita.
With the dataset prepared and optimized, we moved on to selecting the model. After considering several options, we chose XGBoost for this project. XGBoost stands for Extreme Gradient Boosting. It's an advanced implementation of gradient boosting which combines multiple weak learners like decision trees to create a robust predictive model. Here's why we chose this. It is renowned for its speed and accuracy, making it ideal for handling high dimensional datasets like ours. This is especially useful in sensor data, which tends to be complex and multifaceted. It also incorporates techniques to handle imbalanced data, ensuring fair treatment of all activity classes. Um, Other key features of XGBoost include that it has inbuilt regularization, which prevents the model from overfitting, a common challenge in machine learning. It uses parallel processing, which speeds up training significantly compared to other models. It's versatile, excelling in both classification and regression tasks. Let's dive deeper into the architecture of XGBoost and what makes it stand out. At its core, XGBoost is built on gradient boosting framework. This means each tree is designed to minimize the errors known as residuals from the previous ones. It's a step-by-step learning process where every new tree corrects the mistakes of its predecessors, resulting in an ensemble of models that work together for accurate predictions. XGBoost also supports a wide variety of loss functions. What's really clever is its ability to handle imbalanced data by assigning weights to different data points. This ensures that rare classes, which might otherwise be overlooked, are given the attention they deserve. Another feature that stands out is tree pruning. XGBoost doesn't stop splitting a tree prematurely. Instead, it builds the full tree first and then prunes it back, removing unnecessary splits to make it simpler and more effective. The algorithm is also sparsity aware, meaning it's great at handling missing values, if any. And to avoid overfitting, XGBoost employs two types of regularization: L1 to encourage sparsity, and L2 to shrink overly complex models. Together, these ensure that the model generalizes well to new data. And finally, XGBoost isn't just about precision, it's about speed. It parallelizes to tree construction, uses advanced memory optimization, and can even leverage GPUs, making it one of the fastest and most efficient algorithms for large scale data. After selecting XGBoost as our model, the next step was training and evaluating it. We divided the dataset into training and testing splits with an 80-20 split. To optimize the training efficiency, we used the PCA reduced dataset, which significantly decreased training time without compromising the integrity of the information. To achieve the best results, we performed a grid search to fine tune the model's parameters, such as the number of trees, depth, and learning rate. We evaluated the model using various metrics: accuracy to assess overall performance, a classification report to analyze precision, recall, and a fun score for each activity, a confusion matrix to visualize correct and incorrect predictions across activity classes. In this stage, we evaluated the performance of our fine tuned XGBoost model. After an extensive grid search, we identified the optimal hyperparameters: a learning rate of zero point 0.1, a maximum tree depth of 7, and 100 estimators. These parameters allowed the model to achieve an impressive accuracy of 88.8% on the test data. Beyond accuracy, the model showed high precision and recall for most activities, particularly excelling in stationary activities like lying and sitting. However, some misclassifications occur in activities with overlapping features such as walking and stair climbing. The confusion matrix provided a detailed look at prediction errors. For instance, transient states, which was ID0, had some misclassifications as walking, which was ID4, indicating areas of potential refinement. Finally, we analyzed feature importance as visualized in the bar plot. Certain features, such as those from accelerometer and gyroscope sensors, were the most influential in determining activity predictions. These insights underscore the model's capacity to focus on relevant patterns while ignoring redundant information. In summary, our project showcased the potential of using sensor data to accurately identify various human activities. From lying down to running, our model demonstrated its ability to differentiate between these actions with impressive accuracy. This opens up exciting opportunities for applications like fitness tracking, health monitoring, and even rehabilitation programs. Looking ahead, there's immense potential to make this technology even smarter and more personalized. While we have taken a significant step forward, this is just the beginning, and the possibilities for innovation in wearable technology and intelligent systems are vast. And we're excited to see how this work can evolve to make a real world impact. So that is it. Thank you for watching.